All right, so my in-class video recorded, but the audio that I recorded along with it did not, and so the problem with that is then the video and the audio get out of sync on the video that I record, so I have to re-record everything. So I am going to do that here real quick. Sorry for those of you that are using this video to catch up. You still should get all the relevant information and stuff like that. It'll just be at a little bit quicker pace, so that way I can get into other things I need to do today too. But anyway, so that being said, okay, what we talked about today were sequences and series. I guess we started with just sequences today. That's our new unit. All right. Let's see if we get that show. There you go. Okay. So a sequence is any function whose domain is the set of positive integers. However, it is common to represent sequences in subscript notation as shown below. So for example, if you see a sequence, okay, which is just a list of numbers, okay, that are related by some sort of formula or rule, 1 would associate with then a sub 1 because it's the first term here. 2, the second term, would be a sub 2, the second term in the sequence. 3 would be the third term in the sequence, so on and so forth, on down to n, where it's a sub n, right? And then the name for the sequence, we describe it as the braces and then a sub n, like that, around that rule. Okay? So we then look here at our first question, where we have we're asked to write the first 5 terms of the following sequences, right? So I did the first one here pretty explicitly, I guess I'll say, right, where I just kind of like, okay, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and then we actually just took turns then. When n was 1, right, we plugged the 1 for the n right there, and so we got negative 1 to the 1, which is then going to be negative 1 plus 3 gives us negative 2, or sorry, negative 1 plus 3 gives us a positive 2, right? Okay, and then when a sub 2, right, our next term there, second term, all right, n was 2 there, so negative 1 to the 2 is now going to be positive 1, plus 3 gives us 4. Okay, then for the third term, n is now 3, so it'll be negative 1 to the third, which becomes negative 1, plus 3 gives us 2, and you can see we're just going to be swapping, we're going to switch, alternate, toggle, whatever you want, back and forth there between the 2, 4, 2, 4, 2, like that. Okay? And so there's our sequence. Okay, first 5 terms at least. All right. I had the class do, I did like letter C with the class, and then I had them do B and D, but I'm just going to run them through here real quick. So, if you want to try some of those on your own, feel free first, pause the video, and then, start it back up as I explain these. Letter B, though. Again, I just started doing these here, so B1, B2, B3, B4, B5, right? Again, just plugging in 1, 2, 3, 4, and 5 for n for each one of these terms, all right? So it's B, well, you can see it right there. 1 over 1 plus 3 times 1, which is going to be 1 over 4. 2 over 1 plus 3 times 2, which is 2 over 7. 3 over 1 plus 3 times 3, 3 tenths. 4 thirteenths, 5 sixteenths, so on and so forth. Okay. C introduces a symbol that you maybe haven't seen before, or maybe it's been a while since we've seen it, right? N factorial, right? That little exclamation point means n factorial. And just a quick introduction to it, okay? N factorial, so 0 factorial we define to be 1. 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is, 5 times 4 times 3 times 2 times 1, or 1 times 2 times 3 times 4 times 5, which is 120. So you see the idea is, right, when you do the factorial of a number, normally just a positive integer, you then multiply by all the positive integers down to 1. Okay, and that's how you evaluate a factorial. So then evaluating this, well, the numerator here, it's just going to switch between 1 and negative 1, right, depending on what power you've got here. So you go 1, negative 1, 1, negative 1, 1, okay? And then for the n factorial, well, again, first term, 1 factorial is 1, 2 factorial is going to be 2, 3 factorial gives you that 6, 4 factorial gives you 24, and then 5 factorial gives you 120, so on and so forth. And then there's D. I think you get the idea there. No need for explanation. First 5 terms. Okay, again, pause the video if you need to kind of like really soak it in, but yeah, I won't do that. We'll keep going. So, of course, we want to not only be able to like describe a sequence, right, list it out, but we also want to kind of get a better understanding of its behavior as well, like what it does. And so, for example, we want to be able to evaluate the limit of a sequence. One major purpose of sequences is to see if the terms approach a certain value as the terms go on forever. Oops, I'm kind of zoomed in there. Let me see if I can see. There we go. Okay, these sequences are said to converge if there is a single value that our sequence tends to approach as the terms go on forever. Okay, that's a convergent sequence. And so we take our sequence here, 1 over 2 to the n, and we'll write out a few terms here. Okay, n equals 1, 2, 3, 4, and 5. And then we'll see, as we go on to then n equals infinity, as n approaches a really large number, we expect to have then 1 over infinity, right? Okay, right there. And so then what does 1 over infinity approach? Well, that converges to 0, right? Because our denominator increases without bound, the numerator stays 1, and so we're going to go to 0. Okay? And so 0 is what we converge to be. All right. Then the definition of the limit of a sequence. So we kind of just took took a limit, didn't we? We had n approach infinity there, and that's what this is. Okay? So let L be a real number. The limit of a sequence, a sub n, is L, written as the limit as n approaches infinity of a sub n equal to L. And if the limit exists, then the sequence converges to L. If the limit of a sequence does not exist, then the sequence diverges, right? So limit exists, we have a convergent, or the sequence converges. Limit does not exist, the sequence diverges. Okay. Additionally, let L be a real number. Let f be a function of a real variable such that the limit as x approaches infinity of f of x is L. If the sequence, a sub n, is a sequence such that f of n equals a sub n, so in other words, if you can take your sequence and write it as like a function kind of rule for every positive integer n, okay, then the limit of that function will be the same as the limit of that sequence, right? Which is essentially what we just did right there. I mean, you can imagine taking the limit of this 1 over 2n as a function as n approaches infinity. That limit will be the same then as the sequence's limit as n approaches infinity. The difference, right, is that for the function, n is real numbers, all the real numbers, okay, whereas in a sequence, n is just positive integers, so 1, 2, 3, 4, 5, 6, 7, so on and so forth. Anywho, determining whether each of the following sequences converge or diverge. So looking at A and B, we'll start with A here. Okay. Looking at A, okay, and trying to take the limit as n approaches infinity of this thing, we'll notice that that 3 is going to stay 3, but -1 to the n will keep alternating or oscillating maybe between -1 and 1, right? If n is even, this will be positive 1. If n is odd, this will be -1, and so we're going to oscillate between 2 and 4. This is the sequence we saw earlier in the notes. So each term of the sequence is 2 or 4, so then what does that approach? Well, that's just it. It's going to be 2 or 4, but since we can't ever determine which one it ultimately will approach, the limit does not exist, sequence diverges. So in other words, the sequence does not need to go to infinity in order for the sequence to diverge. It could just kind of oscillate or jump between two numbers, and then again, we wouldn't be able to identify a single number that it approaches. And so we say the limit does not exist, and therefore the sequence diverges. Okay? Letter B, right, if we try and do limit as n approaches infinity of this, we get infinity over infinity, which is indeterminate, and so therefore L'Hopital's apply. So we apply L'Hopital's, we get now 1 over 3, and we take the derivative of n is 1, derivative of 1 plus 3n is 3, and so we get 1/3. So the sequence converges then to 1/3. Oops, I'm off the screen, there we go. Okay, and of course you can also see this here in our rules we talked about, maybe back in pre-calculus when we talked about rules for horizontal asymptotes and stuff like that. The limit as n approaches infinity. You can see the degree of the top is 1, the degree of the bottom is 1, so it's the ratio of the lead coefficients 1/3. You can see that there too, without having to actually do L'Hopital's rule. But again, for correct justification's sake, we're going to use L'Hopital's. Right. Moving on. So then for C, D, E, and F, we're going to be using that same principle of taking the limit as n approaches infinity of each one of these. So again, if you want to kind of pause the video here and tackle some of these on your own, you should be good. D and E are pretty straightforward. C, there's like a little thing to it, and I'll show it to you here right now. But D and E are pretty straightforward, so we'll get to those when we get to them here. So C introduces this cosine of n theta, which is like kind of funky to think about. Like, oh man, we got to deal with like trig and stuff like that. But really, if you just think about what is cosine of n theta going to do, remember we're in a sequence here, so n is going to be a positive integer. So we're going to go like n will be 1, n will be 2, 3, 4, 5, so on and so forth. Well, if you take cosine of 1 n, or 1 pi, right, if n equals 1, cosine of pi is -1. Okay, but then cosine of 2 pi would be the next term, that'll be a positive 1. And then cosine of 3 pi, -1. Cosine of 4 pi, +1. And so what's this going to do? Well, this is just another way of saying -1 to the n. Okay? So when we go to do our limit here, we see we end up with infinity plus or minus 1, because again, that cosine n pi is going to be like plus or positive or negative 1 in either case. So we're going to go to infinity for the 3 to the n. And then over 2n squared, that's also going to go to infinity. And so we have infinity plus or minus 1 over infinity. That's indeterminate. L'Hopital's rule applies. So we take the derivative here. Derivative of 3 to the n, that is a rule that we know. We haven't used it a whole lot, but it is a rule that we should know. Derivative of 3 to the n is 3 to the n again. So kind of like e to the x, right? 3 to the n is 3 to the n. But then you multiply by the natural log of your base, natural log of 3 here. Derivative of cosine is negative sine, and then the negative sine n pi, but then times the derivative of what's inside, so that's why I put the pi in front there. Derivative of 2n squared is 4n. Again, n approaches infinity, n approaches infinity. Now it's going to be infinity plus or minus 0, because again, sine of n 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, those are going to be all zeros. So infinity over infinity. Again, L'Hopital's apply, it's indeterminate. Take the derivative once again. This does not require a product rule because it's just a constant. That natural log of 3 is a constant, so you can just take the derivative of 3 to the n again. 3 to the n times natural log 3 squared. Derivative of sine is cosine, so it'll be pi squared cosine n pi all over 4. Okay? And then again, n approaches infinity. Here now, though, the denominator is no longer infinity, it's just 4. The numerator, though, is infinity plus or minus pi squared, which would yield infinity in the numerator, so this goes to infinity, diverges, right? This is no longer indeterminate, okay? We can determine it goes to infinity. So it diverges. All right, letter D, I'm not going to say too much about this one here, so you can just kind of pause it and take a look at that one, okay? It's just using L'Hopital's rule several times until we get to the point where the numerator, goes down to just 2. Okay. Do make sure you're applying those writing apply L'Hopital's and showing that it is indeterminate each time when you apply L'Hopital's there. That's an important part of your analysis. Okay. Letter E. This is a little bit weird, but it's not too bad. Again, take the limit as n approaches infinity of cosine of 3 over n. All right. We can first evaluate just what is the limit as n approaches infinity of 3 over n. Well, that's going to go to 0, right? So then evaluating the limit as n approaches infinity of cosine of 3 over n would be the same thing as evaluating cosine of 0. What's cosine of 0? It's just 1. So this is convergent. It converges to 0. I didn't write that the first time around, but or converges to 1, not 0. Okay, so there's that. All right, and then finally letter F. Now letter F involves some factorials, which is a little bit funky, right? If you imagine taking the limit as n approaches infinity of this thing, well, we're going to have this plus or minus, right? Because that's going to keep switching back and forth between positive and negative 1. So we're going to have plus or minus, and then n factorial. Well, infinity factorial is infinity, okay? I mean, we're just going to use that there. So we end up with then infinity over infinity, or plus or minus infinity over infinity, which is indeterminate. Here's the problem, though. We can't apply L'Hopital's here because we're not differentiating or integrating n factorial, right? We don't know how to differentiate or integrate n factorial. So we can't use L'Hopital's rule. What do we do? Well, n factorial is, what would that be written out if we expanded? It would be n, and the next term would be times n minus 1, right? 1 lower, then times n minus 2, dot, 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 and then 3, 2, and 1, okay? Then in the denominator, it would be n plus 2, right, for the first term. Subtract 1, now times n plus 1, times n minus 1, times n minus 2, dot, 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 3, 2, 1 again. Alrighty. Those cancel, or parts cancel, I should say. The n's cancel, n minus 1, n minus 2s, the 3's, 2's, and 1's, the dot, dot, dots cancel, right? We're left with an n plus 2 and an n plus 1 in the denominator, negative 1 to the n in the numerator. Okay, like so. And so then now if we plug in infinity here, the denominator is going to be infinity. The numerator is going to switch between plus or minus 1. So this as a whole is going to go down to 0. And so this converges to 0. Okay. All right, last piece here. Last piece. Ooh, we can do this. So I'm going to zoom in here on some information that I gave. So what we're going to try and do now is kind of go backwards. Where instead of being given the sequence and coming up with the first 5 terms, we're going to be given the first 5 terms and asked to come up with a sequence, which gets a little bit trickier, right? This is like kind of like the integration, you know. In the past, we were given, here's the problem, what are the answers, right, with the sequences. Now we're saying, here are the answers, what was the problem that gives us that, right? That's a little bit trickier to do, just like integration was a little bit trickier than differentiation, right? So, things we're going to look for, right? We're going to look for repeated addition. Repeated addition, right, as you know it, is multiplication. Think about it this way, right? When you were in elementary school, your teacher was like, okay, 2 plus 2 plus 2, right? That's 6. Well, 2 plus 2 plus 2 is 2 3 times. 3 times 2 is 6, right? And so repeated addition, seeing the same number between successive terms being added each time, that means you are really doing a multiplication rule there. And so, for example, if you see plus 3 plus 3 plus 3, then it's 3 times n. Repeated multiplication, we know that as exponentials, right? So if it's times 3 times 3 times 3, we see that as 3 to the n. Constant second difference. So what do I mean by that? Well, if we go over to here real quick, if you see, for example, something like 1, 4, 9, 16, 25, 36, and you try to see, well, what are we adding by each time? Well, we're adding by 3, 5, 7, then 9, then 11. That's like, ooh, that's not repeated addition. Well, it's repeated addition, but it's not by the same number. But the second difference, right? So if we do then the difference of the differences, we see it's 2, 2, 2, 2. So the second difference is constant. Therefore, it is quadratic in nature. So n squared. This is an n squared relationship right here. And then finally, factorial, all right, which is if we see something like 1, 1, 2, 6, 24, 120, 720, that's going to be your n factorial there. Okay, that's going to give away, you know, the relationship for that, if you see that kind of pattern of numbers there. All right, so let's take a look at letter A. I'll kind of like do a deep dive on letter A, and then we'll maybe, I don't know, we'll see about the other ones here too. Okay, so for letter A, let me do a deep dive letter A and letter B, and then maybe talk about F some too. Anyway, okay, here we go. Letter A. So if you look here, right, this is the first term, second term, third term, fourth term, fifth term. You'll notice here that our 4 terms, the last 4 terms here, all are fractions, but 4 was not. So we made it a fraction to kind of make it match its friends there to kind of help us out. 4 over 1 as opposed to just 4. So again, I labeled them too. First term, second term, third term, fourth term, fifth term. So you can see here in the numerator, what's happening is we are multiplying by 2 each time, right? Times 2, times 2, times 2, times 2. So we're multiplying by 2. That's repeated multiplication, so it's 2 to the n. Okay? On the denominator, we're starting with 1, and we go times 3, times 3, times 3, times 3. So it's multiplied by 3, so it's 3 to the n. But the problem, if we use this as our rule, here, the problem is going to be that if we start with our first term, if n is 1, then that gives us 2/3. But if we look up here, we need a 4 over 1, not a 2 over a 3. So how can we fix that? Well, how can we make 2 be 4? We could multiply it by another 2. So take 2 times 2 to the n in the numerator. And then again, if we want 3 to be 1, how can we make it a 1? Well, multiply by 1/3. So 1/3 times 3 to the n. Okay, which let's see if that works, right? So if we plug in 1 now, it'll be 2 to the 1, 2 times 2 is 4, 4. 3 to the 1, 3 times 1/3 is 1, 4 over 1. Let's try the second term. 2 to the 2, 4 times 2 is 8. 3 to the 2 is 9, times 1/3 is 3, 8/3, and so on and so forth. You can see for the rest there it works. Okay? So you could stop here and say, okay, there's my answer. That's what it's going to be. But let's simplify the sum. For example, write 1/3. That's 3 to the negative 1. So I can rewrite that as 3 to the negative 1. But aha, now we're multiplying two things that have the same base. They both have base 3. So we add our exponents. 3 to the negative 1 times 3 to the 1. Negative 1 plus n, 3 to the n minus 1. Same thing here with the 2's, right? Same base. Add the exponents. So we could say that's our answer. Okay? Or we could say 2 divided by 1/3. 2 divided by 1/3, that's the same thing as 2 times 3. It's 6. And then 2 over 3, both of those to the n, 2/3 to the n. So we could also say 6 times 2/3 to the n. Same idea there. Same idea. Okay, and there's other ways to represent that as well. Okay. Letter B, looking at that one, okay, you'll see it's first alternating, right? Negative, positive, negative, positive, negative. So again, we'll hold off on that maybe, and let's just focus on what's happening in the numerator. So 3, 9, 27, 81, 243, those are clearly multiples of 3. So 3 to the n. Sorry, powers of 3, so it's 3 to the n there for our numerator. Denominator, you see the 1, 2, 6, 24, 120. Where do we see that happening? Right there. It's factorial. Okay? So we'll do 3 to the n over n factorial. Let's see if that works without that right now. So the first term, 3 to the 1, 3. 1 factorial is 1. Let's try the second term. 3 to the 2 is 9. 2 factorial is 2. Let's try the third term. 3 to the third is 27. 3 factorial is 3 times 2 times 1, 6. Aha. And you can go on from there and so on and so forth and see that. Okay? Now we need to also alternate. How do we do that alternating thing? Well, you could use the cosine one that we saw earlier, but this negative 1n is helpful as well. Okay? So let's make sure, though, it's going to work, though. Negative 1 to the n. If I put in my first term here, and if n is 1, it'd be negative 1 to the 1, which is negative 1, and aha, we do need our first term to be negative. If I put a 2 for my second term, negative 1 to the 2 is negative 1 squared, which is positive 1, that is positive, and so on and so forth. It works for the rest. Okay? Of course, that's one way to write it, but you could, since these both have an exponent of n, you can multiply those together and make it negative 3 to the n like that as well if you wanted to simplify it some. Okay? So you guys go ahead, try letters C and D and E. I think you should be fine with those. I'm not going to explain them. I will like briefly kind of show them here. So if you want to pause right now, try C, D, and E. Okay, so I'm going to assume you tried C, D, and E. So here we go. Letter C is that. Again, here it's a constant second difference, right? We're adding 3, 5, 7, 9, so it's then 2, 2, 2, 2 for the second difference. So that's going to be n squared. But if we just use n squared, again, for first term, 1 squared should be positive 1, not negative 1. For second term, 2 squared should be 4, not 2. 3 squared should be 9, not 7. So these are all 2 less than what we need. So we'll take that n squared and subtract 2 to make it work, make it fit there. Okay, fifth term. 5 squared, 25, minus 2 gives us 23. Okay, letter D. This one's very straightforward, I think. Just we're multiplying by 2 each time in the numerator, so it's 2 to the n for the exponent, or sorry, 2 to the n for the numerator. And then we are adding 2. So it's a constant addition, repeated addition here, plus 2, plus 2, plus 2. So it's going to be 2n, but then again, 2n, we have to subtract 1 to make it kind of fit here, right? It's 2n minus 1 there. 1, 3, 5, 7, 9. Okay. E, there's E. Just repeatedly multiplying by x minus 2, and then the denominator is repeat its multiplication by 2 as well, or multiplication by 2, so it's just 2 to the n, x minus 2 to the n. And again, you can combine those together under a single n power there if you wanted to. And then letter F, if you look at the denominator, it's 1, 1, 2, 6, 24. That's n factorial. But if you just use n factorial, again, for the first term, it will work. 1 factorial is 1, but then for the second term is n equals 2. 2 factorial should be a 2 here. And then 3 factorial, this should be 6. And then 4 factorial, this should be 24. And then 5 factorial, this should be 120. So we're like one more ahead here. So what we're going to do is take our n, our term number, subtract by 1, and then do the factorial of that. So for the first term, it'll be 1 minus 1, 0. Factorial is going to give us a 1. For second term, 2 minus 1, 1. 1 factorial gives us 1. Third term, 3 minus 1, 2. 2 factorial, 2. Fourth term, 4 minus 1, 5. 5 factorial, 6. So on and so forth. You see it works for the denominator. Now what's happening in the numerator? Well, we start with 1, then we get x, x squared, x cubed, x to the 4th. So we're repeatedly multiplying by x here. So we might think, oh, it's going to be x to the n. But if it's x to the n, our first term should be an x here, right? X to the 1, and then x to the 2, and then x to the 3. So again, you can see we're always one power back. So you want to do x to the n minus 1 there. Kind of correct that. And of course, we're alternating here. So you might think, oh, let's use negative 1 to the n, but be careful. Negative 1 to the n gives us a negative first, then positive, then negative, then positive. If we want it to be positive first, then negative, we're going to have to make it either negative 1 to the n plus 1 or negative 1 to the n minus 1, one of those two. Okay? And then that'll work right there for us. Okay? And so here, if you make it negative 1 to the n minus 1, then you can combine these two together under this to make that. And that's all I have to say about that. Okay, the homework is posted to Google Classroom. If you have any questions, please talk with Mr. Goff or myself. And good luck. Hopefully this video worked better. And of course, it was much shorter too.